Welcome to Net 201, Network Foundations. I'm Alan Halakmi, Director of Solutions Architecture for Worldwide Public Sector at AWS. And I'm fortunate to be joined today by...
And I'm Madhura Kale, and I'm a Product Manager in Amazon EC2 Networking.
Let's take a look at our agenda for the session. This is a 200-level session designed to provide you the basic building blocks for networking in the AWS cloud. We do expect that you have some familiarity with network concepts and technologies like CIDR notation, DNS, IP routing, and security. Our approach to this session is to break down foundational components in the physical world, translate those into virtual and logical ideas and concepts, and then synthesize those into sample use cases that you can use. Let's start then with a view of the AWS global infrastructure. The AWS global network is built with multiple redundant 100 gigabit Ethernet links and connects 6 continents. Because AWS operates the entire network, we are able to deliver a purpose-built, encrypted, highly available, low latency infrastructure for our customers. This infrastructure connects AWS regions. A region is a geographic area where we cluster data centers. Each region is designed to be isolated from other AWS regions, achieving the greatest possible fault tolerance and stability. In addition, our global network includes hundreds of edge locations for latency-sensitive applications using Amazon CloudFront for content distribution, Amazon Route 53 for domain name service, and AWS Global Accelerator for network path optimization. We group data centers within a region into fault-isolated clusters we call availability zones, or AZs. Each region has multiple availability zones. An AZ consists of one or more discrete data centers, each with redundant power, networking, and connectivity, housed in a separate facility within a region. Our AZs interconnect with high bandwidth, low latency networking over fully redundant, dedicated metro fiber, providing high throughput and low latency networking between availability zones. Each AZ is physically separated by a meaningful distance, many kilometers, from any other AZ. So you can leverage synchronous replication, for example, between AZs to better isolate and protect your workloads from potential issues such as power outages, tornadoes, and floods. AZs are foundational for AWS, and our regional services were designed from the ground up to leverage them. Data centers within an availability zone interconnect over 100 and 400 gigabit Ethernet using an AWS-designed high-density fiber cable. An AWS data center contains racks, and racks contain hosts. Hosts connect to local data center infrastructure, including our highly optimized network fabric, capable of delivering hundreds of petabits per second of bandwidth. Traffic on our network is automatically encrypted before it leaves our secured facilities. From a physical infrastructure perspective, customers tell us they want a continuum of consistent cloud services that extend from regions to network edge, customer premises, and remote locations. They want to operate seamlessly across a multitude of environments, and they want to use the same infrastructure, services, APIs, and tools. AWS Local Zones, AWS Wavelength, and AWS Outposts extend from parent regions to bring AWS services to latency-sensitive edge workloads. AWS Local Zones places select AWS services like compute, storage, and database close to large population industry and IT centers where no AWS region exists today. With AWS Wavelength, we embed AWS compute and storage services within telecommunication provider data centers at the edge of the 5G network. AWS Outposts bring native AWS services, infrastructure, and operating models to your data center, co-location space, or on-premises facility. All three of these offerings can seamlessly access the breadth of AWS services in the parent region. So now that we've talked about the physical infrastructure, let's talk about how you use these components to build your own virtual networks. First, we'll talk about Amazon Virtual Private Cloud, Amazon VPC, your virtual network in the cloud. If you'll recall, AWS regions are geographic areas around the world. Within a region, you logically create a VPC. These VPCs can also extend to local zones, wavelength zones, and outposts in the same parent region. You can have one or more VPCs in a given region per AWS account. Each region has at least 3 availability zones. You can think of each AZ as a singular logical data center. Each AZ is given an alphabetic designation. For example, US East 1A and US East 1B, as shown here. Availability zone designations are selected randomly for each account. That is, your US East 1A might be my US East 1F. If you need resources in the same physical availability zone across accounts, we do expose availability zone IDs so that you can correlate. Subnets within your VPC are bounded by availability zone. You can have multiple subnets within a given availability zone. You can think of the physical hosts as Amazon Elastic Compute Cloud, or EC2 instances. EC2 instances are connected to a subnet through an attached Elastic Network interface. We call those ENIs. Your launched resources, like EC2, are using ENIs as they launch into your VPC. In VPC, we support both IPv4 and IPv6 addressing. So we'll start with v4. With v4, you select and assign a v4 CIDR block to your VPC from size /16 down to /28. This address is considered private by AWS. We recommend customers use RFC 1918 addresses for private internets, though you can bring any IPv4 address you like. Once you set the address for your VPC, you can't change it. So make sure you do the appropriate upfront address planning. Once you define the VPC CIDR, you can assign subnet CIDRs. Remember that subnets are bounded by availability zone. Like VPC, v4 subnets can be between /16 and /28 in size. On the diagram, a public subnet just means that the subnet has a route to an internet gateway, and we'll talk a bit more about that coming up. The v4 addresses you use inside the VPC, the private addresses, they can be assigned by AWS automatically or manually by you. For EC2, you can assign secondary IPv4 addresses on a given ENI, and you can also attach multiple ENIs to a given instance. If you didn't quite get your addressing plan right, we also support secondary v4 CIDR ranges on your VPC. Note that there are 5 reserved IP addresses in each v4 subnet, including the Route 53 resolver at the base of the VPC plus 2. Okay, so that's private addressing, but what about public v4 addresses? You can use public v4 address space from AWS, or you can bring your own IPv4 addresses and select AWS regions. In both cases, you can assign public v4 addresses to your EC2 instances automatically at resource launch, or you can associate them with an elastic IP address. With auto assignment, you cannot move the address between resources. With elastic IPs, you can. Importantly, in v4, the public IP address is not actually assigned to your network interface. Public v4 addresses are mapped using one-to-one NAT as traffic leaves the VPC for the internet, and we'll talk more about that in a bit. If you look at the network configuration in your EC2 instance, you won't see the public v4 address configured. However, you can introspect on the instance using the instance metadata service to find the public v4 address. Now let's talk about v6, both dual stack and IPv6 only subnets in VPC. With v6, you don't select the size of your VPC or subnet CIDRs. v6 VPCs are /56 in size, and the subnets are /64 in size. Subnets can be IPv4 only, they can be dual stack, or they can be v6. Your v6 addresses are global unicast addresses. Unlike v4, the same global unicast address is used for communicating both with internal networks and the internet, as v6 is designed for end-to-end connectivity without network address translation. v6 addresses you use inside the VPC can be auto-assigned by AWS or manually assigned by you. Like v4, the first 4 v6 addresses and the last v6 address in each subnet is reserved. VPC router address is learned by router advertisement and uses the address based on its virtual MAC address. Like v4, you can use AWS IPv6 space or bring your own IPv6 addresses in select AWS regions. Today, we do not support multiple IPv6 CIDRs for your VPC, nor do we support elastic IPs for IPv6. One final and important note about your dual stack subnets. If you exhaust your v4 address space, you will be unable to launch new resources into the subnet, even though you'll have plenty of v6 address space remaining. Because your EC2 instances use global unicast addresses, in addition to the link local address, you will see the global unicast address on the network interface. You can also see here the VPC router's link local address, which is learned via router advertisement. Now that we have some instances with IP addresses, let's talk about routing. Each VPC subnet is and must be associated with a subnet route table. This association can be implicit, that is automatic, or explicit. As you create subnets, there is a main VPC route table that the subnet is automatically associated with. This association ensures that every subnet has a route table. By default, this route table will contain only a route for the local CIDRs, v4 and v6 of the VPC. However, you can create custom VPC route tables and explicitly associate subnets to them. You can associate each subnet with exactly one subnet route table, but a given subnet route table itself can have multiple subnet associations. You use these route tables to control traffic leaving a subnet, and we'll talk more about that in a bit. Each subnet has a VPC router. When an instance in one subnet wants to talk to an instance in another subnet of the same VPC, it forwards the packet to the VPC router on that subnet. The VPC router looks at the VPC route table, sees the next hop as part of the local network, and forwards the packet to the target subnet and onto the instance. Importantly, there is no single physical device that is the VPC router. Rather, the VPC software takes care of packet forwarding for you. As shown in the top route table, you can add a more specific route to provide so-called east-west traffic filtering should you need or desire to do so. Now that we have our VPC, subnets, and routing set up, let's look a bit further into our EC2 instances. First off, you should know that there are local instance services accessible on your EC2 instance. Three that you should know are the EC2 instance metadata service, the Amazon timesync service, and the Amazon Route 53 resolver. The instance metadata service, or IMDS, allows you to introspect on the metadata of an instance. For example, if you provide user data during launch, this information is available through the IMDS. Another example is instance roles. This is a powerful capability of AWS Identity and Access Management where you can grant permissions to an EC2 instance, for example, to access objects in S3. The temporary rotating credentials used for instance roles are accessible through the IMDS. The v4 address is shown here. For v6 on Nitro instances, you can use an IPv6 endpoint, which you will need to explicitly enable. Nitro is the underlying platform in our next generation EC2 instances, and it's available today on over 36 of our instance types. The Amazon timesync service provides NTP endpoints to a fleet of satellite-connected atomic reference clocks in each AWS region. Of note, Amazon timesync service will automatically smooth any leap seconds that might be added to coordinated universal time. The v4 and v6 addresses for Nitro instances are shown here. Finally, Amazon Route 53 is AWS's managed DNS service. Within your VPC, you can use Route 53 Resolver to provide domain name service. This service is available at the base of the VPC CIDR plus 2. It's also available at the v4 and Nitro v6 addresses shown here. From a networking perspective, security for VPC is available at 3 coarse-grained levels: traffic exchanged across the instance network interface, traffic exchanged across the subnet, and traffic exchanged across the VPC boundary. You'll see an icon that I've popped up here in the right corner. If you're a security type, that's your indication that we're going to talk about something that you should pay attention to. So just keep an eye out for that as we go through. Security groups are stateful firewalls that you put around an instance. Well, more accurately, you put them around an elastic network interface, but We'll stick with instances for simplicity. This is your most fundamental tool for network protection of resources in your VPC. By default, inbound security group rules deny all traffic. So if you wanted to allow SSH to your EC2 instance, you'd create an inbound security group rule to allow it and associate that security group with your instance. Inbound traffic to TCP port 22 is now explicitly allowed from any source IP. And because security groups are stateful, the outbound packet is automatically allowed as well. Security groups also have outbound rules. By default, these allow instance-initiated traffic outbound. However, let's say you wanted to restrict new outbound SSH connections to only a specific IP destination. You could update the security group outbound rule. Now, new connections outbound are allowed by the rule only to that specific IP address. And because security groups are stateful, the return traffic is also allowed. Now that we have a security group that we like, we can associate it with multiple EC2 instances. A typical example would be when you use EC2 autoscaling. As a scale-out event occurs, the new instances are automatically included in the security group you define. In this way, you have a consistent network perimeter at the instance and ENI level. Interestingly, though, instances within this security group can SSH to one another, but that's it. They can't ping one another, for example. In your security group rules, sources for inbound and destinations for outbound, they can reference a specific IP address, a group of IP addresses using an abstraction we call a prefix list, or they can specify a security group. Each security group has its own security group ID. So within a given security group, you can reference that security group ID to control traffic between instances within that security group. With this additional inbound security group rule, I've allowed all traffic between instances within this security group. The ability to reference security groups as a source or destination is an important tool for you in managing the security of your VPC. Take, for example, a basic web architecture. Users want to access your web server using HTTPS over TCP port 443. You set the inbound security group rules for your web server security group to allow the HTTP traffic from all sources. Bidirectional traffic can now flow to the web server. However, your web server also requires backend database access to Amazon RDS Aurora over TCP port 3306. So we create a separate security group for the database. And we allow TCP 3306 inbound from the security group for the web servers. Now, any instance within the web server security group is allowed to access instances within the database security group. Going back to the autoscaling example, this means that as you add new web servers, they are automatically able to communicate with the database server. You don't have to track IP addresses or input subnet side ranges that cover blocks of unused IPs. Similarly, when you add a secondary database server, traffic continues to flow without having to update security group rules. Now that we've covered the instance interface boundary, let's talk about the subnet boundary. Network address control lists, or NACLs, wrap your VPC subnets and provide stateless packet filtering. So you'll need to define rules in each direction of traffic flow. By default, NACLs allow all traffic into and out of your VPC. Like route tables from earlier, every subnet must be associated with a NACL, and a given NACL can have multiple subnet associations. In our previous example of SSHing into an instance, the inbound traffic was allowed because our inbound NACL rules allow the traffic. Since NACLs are stateless, we also need an outbound rule that allows the traffic. Because we're using the default NACLs here, the traffic outbound is also permitted. The connection setup succeeds. However, if we modified the outbound NACL, removing the allow statement, the default deny rules would prevent return packets from leaving the subnet, and the connection setup would fail. Like security groups, you can be specific on the allowed sources and destinations, though you can only use IP addresses. In this example, I only want to allow a specific SSH client to access my EC2 instances. I define an inbound rule with the specific source IPs and target port, in this case TCP/22. The outbound rules likewise need to reference the specific destination IPs and target ports. Because NACLs are stateless, I need to allow the ephemeral port range that will be in the return packet so the connection setup will succeed. Now that we've talked about network traffic at the instance and interface and subnet boundary, let's talk about the VPC boundary. In the diagram, we see on the left the web server and the database from earlier. On the right, we see the Bastion server and the monitoring server. I want to SSH to my Bastion server, and from that server, the observability data on my monitoring server. I try to SSH to the Bastion, but the connection never crosses the VPC boundary. For traffic from the internet to access resources in a VPC, 5 things must be true. First, the target resource must have a public IP address. We have that. Second, the security group must allow the traffic to the instance network interface. We did that earlier. Third, the network access control lists must allow the traffic. We're using the defaults, so all traffic is permitted in and outbound. Fourth, we need an internet gateway. Well, we don't have one, so we'll create one. And fifth, we need a route for our subnets that passes the traffic to the internet gateway. The internet gateway is the bridge between the VPC world and the internet. It provides the one-to-one network address translation between private addresses in v4 and public addresses on the internet. It's also the bidirectional transit point for your IPv6 global unicast addresses. With these components in place, I can SSH into my Bastion instance and reach the monitoring server. Now Madhura will tell you more about peering, endpoints, and gateways, and how the internet gateway can help you.
Nice segue there, Alan. After talking about routing and controlling traffic inside your VPC, we're now going to talk about connectivity outside of your VPC. In peering, endpoints, and gateways, we're going to cover all of these today. Different connectivity options. We have quite a few, and as you can see, one or two of them may be called gateways. We're going to go through each one of those, but first let's pick up where Alan left off at the internet gateway. This is where we had our VPC. I'm going to simplify it a little bit, remove some IP addresses, zoom in so we can create some space and add more. And there you go. You had your internet gateway, you have your security groups and NACLs configured to allow traffic to your instances that are reachable from the internet. And you add a route table. In this route table, I have default routes to the internet via the internet gateway. This way, my instances with elastic IPs and IPv4 or public IPv4 addresses and globally unique IPv6 addresses are connected to the internet. Now, what about instances in my private subnet? Wouldn't it be nice for them to also be able to connect to the internet to download a software update? For that, we have a product called the NAT Gateway. A NAT Gateway is a managed network address translation, port address translation service that allows you to connect outbound only from instances in your private subnets. So for instances in your private subnet, you have a NAT gateway. A NAT gateway helps you connect instances in your private subnet to the internet. The way it works is simple. You have a route, you create your NAT gateways in multiple subnets. Your public subnet route table would then have an IPv4 default route to the internet gateway and an IPv6 default route to the internet gateway. The private subnet will have a separate route table, and that one will have a default route not to the internet gateway, but to the NAT gateway this time. And this way, your private subnet will, your private instance in a private subnet will first get to the NAT gateway. The NAT will translate to the private IP of the NAT gateway, and then send it over to the internet gateway where it picks up the elastic IP of the NAT gateway and is off to the internet. Now, I said something about private IP of the NAT gateway. So NAT gateway supports a private connectivity type as well, where instead of going to the internet, you could very well be just connecting to another IPv4 destination, but really want that network address translation that NAT provides. Now, NAT gateway is catered for IPv4 destinations. What about IPv6 internet? Is there a way to have outbound only connectivity that is to an IPv6 world? Yes, there is. I wouldn't have planted that question if there wasn't. For that, we have something called an egress-only internet gateway. An egress-only internet gateway, think of it as a marriage between internet gateway and NAT gateway. It is created as one per your VPC instead of in subnet, so very much like an internet gateway. But like the NAT gateway, it provides outbound only connectivity. The way you do it is you create a route table in your private IPv6 subnet where the default route, instead of pointing to the internet gateway, points to the egress-only internet gateway, and you're off to the internet. Now you're asking me, we talked about many of these things to connect to the internet. Do I need to choose? No, you don't. You can actually have all of these. The configuration in the right gets you with a public subnet on the top and private subnet on the bottom for IPv4. And similarly, on the left, you'd want that configuration for a private-public separation in IPv6. Okay, so we've talked about internet gateway and a NAT gateway. Now we're going to move from internet connectivity to connectivity in the private network in AWS. Let's start with the simplest one, VPC peering. Now, your private network may not be limited to a single VPC. You could separate applications, you could separate organizations logically using separate VPCs. But then sometimes you also like connectivity between them. So over here, I've separated my single VPC into two. I can use VPC peering to connect these two VPCs together. A VPC peering connection is a one-to-one connection between two VPCs that allows two VPCs to operate like they're part of the same flat network. All you do is create a peering connection between two VPCs and update route tables on both sides, on both VPCs, to point to the peering connection for your neighbor VPC CIDR. And once you have that, your peering connection is set up and running. Instances in each VPC can talk to all the instances in the peered VPC. There is no internet gateway needed. This doesn't rely on separate hardware. It is just built on existing AWS infrastructure. One thing to note is that with VPC peering, you cannot have overlapping IPv4 CIDRs. Now, you can say, hey, the simplified architecture, maybe I want more VPCs. And you can absolutely have that. You could have 5 over here in my diagram and then have peering connections from one to many. Or you can have a full mesh of many to many where all VPCs are peered together. But as this grows, it can start getting a bit complex. So for that, we have our second way of connecting between VPCs, and that is a transit gateway. A transit gateway is a virtual router that acts as a central hub for all of your VPCs. And when I say all, I mean not tens, not hundreds, but thousands of VPCs. It also provides a hub for hybrid connectivity, which we're going to get to in a bit. There are 3 concepts you need to know about a transit gateway. First is attachment. The attachment is the transit gateway's attachment to a particular resource. In this case, the resource I have picked is VPC. The attachment type could also be a direct connect or VPN or an SD-WAN appliance from a AWS partner. For now, we're going to stick with VPC. You select your VPC ID, you select the subnets, and you're done with your attachment. The next thing you want, the second concept of transit gateway, is a route table. A transit gateway comes with the default route table, but you could have multiple route tables for the transit gateway. The route tables contain static and dynamic entries, with the next hop being one of the attachments of the transit gateway. And that brings us to the third concept that completes the whole thing is the association. Once you have an attachment created and then you have a route table, you then want to associate that route table with a particular attachment. In this case, route table 2 is associated with attachment 2, and it has, for traffic coming into attachment 2, for 10.1, it'll go to attachment 1, and for 10.3, it will be forwarded to attachment 3. Let's see a transit gateway in action. Now, we have 4 VPCs, 1, 2, 3, and 4. VPC 1 is associated with a route table 1 with routes to all the other VPCs 2, 3, and 4. VPC 2 and 3, on the other hand, have only routes to 1, 2, and 3. If you look closely, VPCs 2 and 3 have the same routing table that are associated with their attachment, which means that VPCs 2 and 3 belong to the same transit gateway route domain. And finally, VPC 4 has route table 4 associated with the attachment, and it only has routes to VPC 1 via the transit gateway. As a result, what we've built here is a blue network where everything blue can talk blue, and a purple network where everything purple can talk purple, but blue and purple do not talk to each other. What you can achieve with a transit gateway, therefore, is a very versatile, centrally managed enterprise scale network. You can use Transit Gateway Network Manager to actually control all of these global resources. Now, we've built this privately stitched up network with plenty of VPCs and all our resources, all logically separated and connecting the right way. But when this private network needs to talk to AWS services, for example, an application needs to go right to an S3 bucket, can they do that privately? The answer is yes, with the help of VPC interface endpoints. Interface endpoints help you connect to 130 plus AWS services and over 1,300 AWS third-party partners that also offer services for connectivity. The way it works is simple. You create an interface endpoint in your VPC. You pick subnets that you want the endpoint to live in. What AWS does is creates an endpoint network interface in each of those subnets. And that's it, just like that. Based on the name of the service you provide, the subnet that you have an endpoint created in will have access to that service via that endpoint. This technology is built on an AWS service called AWS Private Link. We're going to talk about that in a little bit, but before, let me tell you about a second type of endpoint that predates Private Link, and those are called gateway endpoints. They are very similar to interface endpoints. I know there are two types, but they're very similar in that you create an endpoint in the VPC. And the two differences are, one is it supports two services only, S3 and DynamoDB. And instead of AWS creating an endpoint network interface for you, what you're going to do is have to update your subnet route table to explicitly add routes for the public IPs for Amazon S3 and DynamoDB. And then once you have that, you're off to connect to these services privately. Without VPC endpoints, so if you didn't want private connectivity to services, you can go the route we started at the beginning of this section, where you have an internet gateway, you have a NAT gateway, and then you update your route tables, and off you go to these services. Doable, but VPC endpoints also come with an advantage. That's that security alert icon. Aren't you glad we have those? VPC endpoints come with VPC endpoint policies. Now, an endpoint policy is nothing but an identity access management resource policy. It does not override your user-based policy or even your service-specific policy, like an S3 bucket policy. It is a separate policy for the endpoint itself to control access to services via these endpoints. Over here, I just have a quick sample where I'm allowing only my IAM role, some role, to access these access services via this endpoint. And now quickly, before we exit this section, we are going to cover Private Link. I mentioned earlier that interface endpoints are built on this technology called Private Link. Private Link conceptually has two sides. One is the consumer side, where you have consumer VPCs, and the other is a service provider side, where you provide the service, you own the application that you want to serve to multiple clients. Now think of this as you running an application, and your customers could be either your own internal customers in your organization, or your customers could be other AWS customers that would be running in their own VPCs. These customers can basically now simply create endpoints in their VPCs and be able to access your application. The application you build is known as the endpoint service. The endpoint service is typically a load balanced application behind a network load balancer. The cool thing about Private Link is, aside from allowing you to offer a service to several clients in different VPCs, you could also offer that same service to your clients in another region, so it extends across regions. And you could also have your service running on premise in your data center, and then use this endpoint service in AWS to serve customers that run in AWS. That was about private connectivity. And now we're going to look at this slide again, where we have covered the internet gateway, the NAT gateway, peering connections, transit gateway, and endpoints. Now, what we're going to talk about next is hybrid connectivity with 3 different services. 3 services offer hybrid connectivity today. One is Direct Connect. It allows high-speed physical connectivity between AWS and your data centers or office locations bypassing the internet. Site-to-site VPN is your IPsec VPN service, managed IPsec VPN service that allows you to connect on-premises locations to your VPC resources, either over the internet or over Direct Connect. And last but not the least is client VPN service that can be used by your remote workers to access resources on premises as well as on AWS. We're going to go through each of these now. Starting with Direct Connect. A Direct Connect is a service that has 108 points of presence around the world, where you can connect your physical data center with an AWS Direct Connect location with a physical Ethernet cable. Direct Connect helps you connect to public services like Amazon S3 and Amazon VPC. The concepts of Direct Connect are: 1, the physical connection. The physical connection is the actual connection you set up between your device on premises and the AWS site device. The physical connection can be 1 gig, 10 gig, and at specific locations, even 100 gig. Then you have virtual interfaces. There's 3 types of virtual interfaces. A virtual interface is basically a slice of that physical connection. It technically is a VLAN on the router that segments your physical connection. The first type of virtual interface is a public virtual interface that allows you to connect to services like S3. And the second type of virtual interface is called a private virtual interface that allows you to connect to your VPCs and private resources in AWS. Now, I haven't drawn that completion line. That's because you need a couple more things to complete that private connectivity. The first thing is a Direct Connect gateway. A Direct Connect gateway allows you to extend your single virtual interface connection to multiple VPCs in multiple regions. So imagine you're sitting here in New York with a physical connection to a New York Direct Connect location, but that same private virtual interface with a Direct Connect gateway will allow you to connect to a VPC out in Japan. And then the third thing is the VPC attachment itself. Over here, I have a virtual private gateway, which a virtual private gateway is a private entry point to a VPC. It's an aggregator of any type of Direct Connect or VPN connection, but it's only 1 per VPC. It predates the transit gateway, and you can attach from a Direct Connect gateway, you can attach up to 10 such virtual private gateways and 10 such VPCs. If you want more scale, however, you'd want a transit gateway. And for the transit gateway, we have a specialized type of private VIF called the transit VIF. And then you do the same thing where the transit VIF attaches to the Direct Connect gateway, and the Direct Connect gateway associates with the transit gateway. If this is confusing to remember, the 2 things you want to take away is private VIF, virtual private gateway, transit VIF, transit gateway. And the last thing I will leave you with on Direct Connect is that at specific locations now, Transit Gateway also supports 802.1ae MACsec standard encryption that provides line rate point-to-point encryption between your device and the AWS Direct Connect device. Our second service for hybrid connectivity is site-to-site VPN. Site-to-site VPN offers IPsec VPN connections. And it has three concepts again. We're going to go through three concepts for everything. Three concepts again. One is a customer gateway. A customer gateway is nothing but an AWS resource you create which provides information of your side of the VPN connection. The second is the connection itself, where the VPN connection is comprises of two IPsec VPN tunnels that encrypt traffic back and forth between your premises and AWS. And the third is the VPN aggregator itself on the AWS side. That could be an AWS Transit Gateway, or it could be a virtual private gateway. Obviously, you know the difference. Transit Gateway will provide you connectivity to thousands of VPCs versus the virtual private gateway will be a single VPC. You can also have multiple site-to-site VPN connections, and all of them terminating to the same aggregator. And last but not the least, our final hybrid connectivity service is Client VPN, which provides fully managed, elastic, and secure TLS connections from any location for your remote workers using the AWS provided client or any OpenVPN based client. It supports split tunneling, so it can get you access not just to your resources on the same local network, but also in AWS. It supports client authentication using Active Directory, federated authentication, and certificate-based authentication. And finally, it also provides client-to-client connectivity. Okay, let's bring this all together. A quick recap. Let's see how many you remember. We started with the NAT gateway and the internet gateway, also the egress-only internet gateway for internet connectivity. Then we connected VPCs using peering and using transit gateways. And then we drew endpoints to connect to AWS services privately. And finally, we did VPN to connect to a transit gateway to connect on premises, optionally direct connect to connect from your data center to AWS. You could also have your data center, if you have a separate one closer to a local zone, you could connect that direct connect as well to a virtual private gateway of the VPC in your local zone. These are all the ones that we covered today. On the top right, the orange square is actually an outpost rack. An outpost rack has its own gateway called the local gateway that helps you connect to your data center network where the outpost rack is located. That's all our gateways. Now, we are going to get into a section where we're done with connectivity, and now we're going to get into application level networking and how you build the right networking for your apps. First up is elastic load balancing. Highly scalable and available applications always require load balancers. AWS offers three load balancing services: application load balancer for flexible application management, network load balancer for layer 4, and layer 4 load balancing with high performance and static IP addresses, and the gateway load balancer when you want to insert third-party virtual network appliances transparently in your network. Load balancing has some key concepts that are broadly applicable to all the load balancers. First is the load balancer itself. It acts as the entry point for all of your clients that are trying to access your application. The second is listeners. You can configure one or more listeners for a load balancer, each of them listening on a port and protocol number. The listeners are also configured with rules, and these rules conditionally take actions on the incoming request, whether it's forwarding or redirecting these clients. The third is a target group itself. The target group is your registered, say, instances, EC2 instances that are actually being load balanced. You have multiple targets, typically in a target group, and you can register a listener with one target group or multiple target groups. And then you can also have a single target as part of two different target groups. And finally, a target group can also be configured with health checks, and the health check periodically check the health of your targets and make sure they're available and able to serve your clients. So what are the differences between these load balancers then? Let's take a look. I'm not going to read through all of these, but on a high level, they operate at different layers, where application operates at 7, network load balancer operates at 4. The gateway load balancer is a layer 3 gateway and does layer 4 load balancing. They all have the same types of targets, whether it's instances or IP addresses. Additionally, application load balancer also supports Lambda function as targets, whereas the network load balancer actually recently supports an application load balancer as a target. The other things I'm not going to read through. The last thing I'll leave you with is, while ALB and NLB terminate flows, the gateway load balancer is a transparent pass-through. Here's a quick look at what an architecture looks like. You create a load balancer. I've chosen the application load balancer. You can choose for this to be an internal or internet facing. That's why I have both the internet gateway and an egress-only internet gateway here. But let's say this is an internet-facing load balancer. It can be single stack IPv4 or dual stack as well. And you then create a target group and you register these targets to the load balancer. In this case, my targets are in my 2 private subnets. These targets can be both IPv4 as well as IPv6. One thing to note about load balancer behavior is, when you create a load balancer, you also choose availability zones and subnets that it should be created in, and at minimum that has to be 2. When you choose these subnets, we actually create network interfaces in those subnets that represent the load balancer. And I mentioned earlier that we support application load balancer as a target of network. Here's what that looks like. You create a network load balancer, you register a target type as the application load balancer, and then the application load balancer load balances HTTP targets. Now that you have a load balance applications, it's not complete without having a cool name that your users can actually reach it on. So for that, we have a Route 53, our managed DNS service. I'm going to talk about some basic concepts of Route 53 first. The first thing is Amazon provided DNS, which is the Route 53 resolver for your VPC. Now, this is not in a single subnet or an availability zone, but it is reachable on 3 addresses from instances in your VPC, 2 IPv4 and 1 IPv6. This resolver is used to resolve queries privately within your VPC, as well as publicly when configured that way. DNS host names. Now, host names, the private DNS name comes with every IPv4 and dual stack instance, and it's IP-based as defined here. A second type of host name that comes that launched recently is a resource-based private DNS name. Instead of IP-based, this one has the instance ID on there, and it resolves not just to the IPv4, but the IPv6 address as well. It also comes with a toggle where you can then enable A or quad A responses on this name if you desire. And the final type of name is a public DNS name. This is optionally enabled if you select the DNS host name and DNS resolution parameters on your VPC, attributes on your VPC, and it allows your instance to be reachable from over the internet. Now, once you have, this is very basics of Route 53 resolver, but you can build much more sophisticated DNS for your application. A couple of things you can do is, one, you can with Route 53, you can have use your DNS resolver on premises in parallel with the Route 53 resolver. So how do you do that? Here's your DNS. Here's your on-premises. It's likely connected via direct connect or some private connectivity. For forwarding queries from Route 53 to your on-prem resolver, you create something called an outbound resolver endpoint. So you can set forwarding rules via this outbound endpoint to reach DNS resolver on premises and get the right IP addresses as a response. The reverse can also be done, where your DNS resolver on premises can use something called an inbound resolver endpoint to then forward DNS queries to Route 53 resolver to reach either your AWS resources like EC2 instances, or look up DNS records in your private hosted zone. Private hosted zones. Now, what's that? That's the first time I mentioned it. A hosted zone is nothing but a collection of records that are associated with one or more VPCs that are in your network. A private hosted zone is for private domains specifically, but you can also create public hosted zones for connectivity connectivity to your app over the internet. The basics of hosted zones include having these DNS records. Over here, I have db.example. I have the domain example.aws and a subdomain here where I have a database server reachable at db.example.aws. What simply happens is an application instance in one VPC will query resolver for db.example.aws. It returns the IP address from the DNS records defined in the private hosted zone, and then the application is able to set up a connection to the database. You would do the exact same thing with public domains. You just have to register those domains, or Route 53 can provide you new domain names as well. Okay, so we created an application, we load balanced it, we have a cool DNS name to it. Are you ready to go? Maybe. Let's talk about optimizing performance for your application. So the first thing is a service called Global Accelerator that helps you improve reliability and availability of your application when you have global users or when your application runs across multiple AWS regions. Let's look at this VPC where I have something running. I'm going to zoom out a little bit. There's your region. This is AWS Cloud. Now, Global Accelerator is a collection of over 96 points of presence around the world. When you create a global accelerator, we give you 2 static IPs. The static IPs are any cast from multiple points of presence around the world that enable your users to find the nearest edge location to hop onto the AWS network and be most efficiently connected to your application. Now, the accelerator can point to your application where it could be an EC2 instance, or an IP address, or a network load balancer, and an application load balancer. The last thing to know about Global Accelerator is that these 2 static IPs actually represent 2 isolated fault-tolerant network zones on the AWS network that do not rely on any do not have any overlap in physical infrastructure in the back end. So if one static IP becomes unavailable for some reason, your users can retry connecting to your application using the other IP, and it is guaranteed to be available always. And now that we have an application where your users can connect easily to, let's talk about actually serving content in large files where, hey, if we have an HTML page that's heavy, or you have images, video, even live video, that's content you're serving and you want to optimize performance for that, we have Amazon CloudFront, which is our content delivery service that helps you minimize your latency for any file downloads via a network of more than 275 points of presence around the world. What Amazon CloudFront does is it creates caches of files that you want to serve and content you want to serve at these several edge locations. So it minimizes latency and gets you faster download time for your users, getting better performance. There's 3 concepts of CloudFront that you should know. The first is something called an origin server. Here it is an S3 bucket. The second, where the origin server is the authoritative source of the file that your users will download. Then you have the CloudFront distribution itself. The distribution is basically the configuration where you decide, hey, this is my origin server, here's where I want to serve my content. The distribution comes with its own domain name, and you can use Route 53 again to create a nicer name. And then the distribution is then, the config file for the distribution is copied and stored at all caches as a record. Now, what happens in reality? Let's say we've configured this distribution. Now we have an application load balancer and an application that's running, and that acts as our origin server right now. a user queries Route 53 on the domain name for the application and is routed to the edge location nearest to it. However, given this is the first request ever after you created the distribution, the user gets a cache miss, and instead of getting routed to the edge location, is routed to the origin server. What the origin server does is responds to the user, but also creates a cache at the nearest edge location to that user, and subsequent requests from that set of users or that geography then are served from the edge location with the lowest latency. Now that we've built highly performant applications, I'm going to hand it off to Alan to cover security for your applications.
Before we end, let's cover some AWS security services you should know about to protect your network. We won't dive into each of these services and features, but it's important that you're aware of and implement them as appropriate. Let's start with distributed denial of service, or DDoS. AWS Shield provides always-on detection and automated inline mitigation to minimize customer impact. Shield provides 2 levels of protection against DDoS: Shield Standard and Shield Advanced. Shield Standard is provided to you by AWS at no additional charge. It defends against the most common and frequent DDoS attacks. Shield Advanced is a subscription-based service where you define specific resources to protect. Shield Advanced customers have 24/7 access to the AWS Shield response team for assistance during a DDoS attack. Additionally, Shield Advanced offers some cost protections against spikes in your AWS bill resulting from a DDoS attack. AWS WAF is a web application firewall that lets you monitor and protect HTTP and HTTPS traffic to select AWS services. WAF allows you to control traffic with allow lists, block lists, or just to count it. WAF provides fine-grained control to inspect a variety of elements of inbound requests. You can create your own rules, leverage AWS managed rules, or use third-party managed rules available on AWS Marketplace. WAF is included at no additional charge for protected resources as part of Shield Advanced. AWS Network Firewall provides a cloud-native, stateful, flexible managed network firewall for your VPC. AWS Network Firewall's flexible rules engine lets you define firewall rules that give you fine-grained control over network traffic. So you don't have to worry about deploying and managing infrastructure. You can import rules you've already written in common open source rule formats, as well as enable integrations with managed intelligence feeds sourced by AWS partners. If you use Route 53 for public hosted zones, you can configure Route 53 to log information about DNS queries it receives. The log contains request information, including date and time of the request, resource record type, and the response code. This information may be useful to you both prospectively and retrospectively. Route 53 Resolver for your VPC also provides a DNS firewall. With DNS firewall, you can filter and regulate outbound DNS traffic from your VPC. You can bring your own domain lists to allow, deny, or alert on, or you can leverage AWS managed lists. DNS firewall allows you to protect against data exfiltration over DNS and name resolution for command and control servers. You can also configure query logging for your Route 53 DNS firewall. Finally, many customers integrate their on-premises DNS infrastructure with Route 53 using Route 53 Resolver endpoints. Using these endpoints, you can also leverage the same capabilities of the DNS firewall. When it comes to understanding network traffic within your VPC, we provide you 2 options: VPC flow logs and traffic mirroring. With VPC flow logs, you can capture information about the IP traffic passing between network interfaces in your VPC. To analyze the data, you can use CloudWatch Log Insights or Athena with Apache Parquet formatted logs in S3 using multiple predefined queries provided by AWS. If you want to receive actual packets, that's when you use VPC traffic mirroring. Traffic mirroring allows you to copy network traffic from the ENI of an EC2 instance and send it to an out-of-band security appliance or monitoring device. This feature is useful for content inspection, threat monitoring, or just plain old network troubleshooting. With traffic mirroring, you set up a target to receive the packets, you define a filter for what traffic should be copied, and you create a session that connects the source and the filter to the target. The mirror target can be the elastic network interface of an EC2 instance, or a network load balancer with a UDP listener. Finally, I want to take a moment to talk about Amazon Guard Duty. Guard Duty is a continuous security monitoring service that analyzes and processes VPC flow logs, CloudTrail events, and DNS logs, even if you haven't enabled them in your account. Guard Duty leverages threat intelligence feeds from AWS and other services, along with machine learning to identify potentially unauthorized or malicious activity in your AWS account. Guard Duty is an easy service to enable. It's low cost and high value. Please enable Guard Duty for all your AWS accounts. Make sure you have automation to action or notify you when findings are generated. On behalf of Madura and myself, thank you